grading these was an interesting experience, and we'll talk all about it momentarily. So after grading all of them, the average turned out to be a 69. So in a what?
Better than the physics class it was kind of
Okay. So and in a bout of mercy, I shifted all the scores up by 8 points, which means that the high score turned out to be 108. So, okay. Okay, so here's what's supposed to happen. I guess the pen's not going to really help me at this point. Well, actually, number one went quite well, so there's not much to say about that one. Because you can split it up into a product of two single integrals. And this one y squared over 2, so you get 1/2. This integral turns out to be 2, so you just get 1 to that. And most people got that one. Okay, but things kind of went awry after that. So the most straightforward way to set up this one, and by the way, I basically, for the most part, the way I said partial credit was I looked at half a points for the setup, half a points for what happened when you integrated it, except of course for the last problem, which was all set up. So if you set it up right, you got a fair amount of partial credit. Okay, so the most straightforward setup is 0 to 2 in x, and then 0 to x squared in y. The y dx, and this one you, because of the variable limit of x squared, you cannot separate these into two single integrals. Although the x you could pull out here. One thing that's a common mistake is, because you all know derivative of sine is cosine, derivative of cosine. Okay. Is minus sine, but since differentiation is integration in reverse, when you're integrating, it's the opposite sign pattern. So integral of sine is cosine, with no sign change. Integral of cosine. I got that totally wrong, didn't I? Yeah. Yeah. So if you take this and reverse it, you get this. So what I see often is people applying the same sign pattern to this, when it's the other way around. So that's one thing. But then once you work out the inner integral, okay, you get to that point. And what are you supposed to do next to work this out? What? Anybody? Substitution. Remember, my hearing sucks. So that works out conveniently to get the answer from there. I still see things like if you have product of functions, people integrating the two individually, multiplying together, things like x squared over 2 or whatever. No. Something like this, substitution is what it's called for. Okay. So any questions about these first two? Okay. For the next one, this is where there was the most difficulty following directions. Polar coordinates to find the volume of a sphere of radius 1. Polar, not spherical. Some people went ahead and used spherical anyway. So if this is your situation looking at the sphere from the side, even if you don't have a picture, I said, I gave a hint, use the equation of a sphere to get your integrand. Because what's happening is the volume, if you're going to be integrating in polar coordinates, so that would be from 0 to 2 pi d theta, and then from 0 to 1 in r, and don't forget your extra factor of r. So that's most of the setup. And the reason why it's 0 to 1 is because the radius of your sphere is 1. So if you take a sphere and you look down on it, down the z-axis, and look at the xy plane, what do you have? It's just a circle of radius 1. So that's why this is your domain of integration. But where a lot of people had trouble was finding the integrand. The integrand here, basically, it has to be z. So think it's x squared plus y squared. In polar coordinates, what does that equal to?
R squared.
R squared. So if r squared plus z squared is equal to 1, so that means that your z value for any given r is the square root of 1 minus r squared. So if you have r going out to here for whatever value of theta you have, and here is your z value, the radius of a whole sphere is 1. So you have a right triangle. But again, even if you don't have a picture, just by taking the equation of the sphere and rewriting it in terms of polar coordinates, you can solve for z. Now, the other thing I mentioned was don't forget to include both the lower and upper hemispheres. So the equation here for z is square root of 1 minus r squared. That describes the upper hemisphere. How do I describe the lower hemisphere? Negative of that. So, because here, you have r squared plus z squared equals 1, you solve for z, you got to take a square root. You have a positive and negative square root. So you have minus square root of 1 minus r squared. So you could think of this as square root of 1 minus r squared minus that. But then these terms just add together. So you can also think of it in terms of doing only the upper hemisphere and then doubling it. And if you remember a formula for the volume of a sphere, 4/3 pi r cubed, at least you know what answer you're supposed to get. And so this is set up, and then just like problem 2, you use a substitution. U is equal to 1 minus r squared, because then du is minus 2r dr, which gets rid of that r. Right. So when you're switching when you're changing coordinate systems, like from Cartesian to polar or cylindrical or spherical or any other, what you want to do is take the boundaries of your domain, like in this case the sphere, and rewrite it in the new coordinates, and that will help get you your integrands or your limits. So any questions about this one? And the final will primarily be on new material, chapter 15, but there will be some questions on this older stuff from test 1 or test 2. So it's really trying to see if you went wrong, where you went wrong, so you don't lose these kind of points a second time. The triple integral setup is straightforward because all the limits are constant. So 1 to 2 in x, 0 to 1 in y, and then 1 to 3 in z, d, dy, dx. Now the z part is the most straightforward to handle because there's nothing in these limits or this integrated depends on z. So you can separate that part out and handle dz. And then you're left with a double integral, 1 to 2, 0 to 1, y e to the xy, dy dx. Okay. Now, this kind of problem came up sort of a homework where it was necessary to switch the order of integration. Because chances are the most straightforward thing you would do is set it up this way. But, okay, so this just turns out to be 2. This one, like you could integrate this with respect to y. But that would require integration by parts. And you really don't want to do that. So I wouldn't say it's impossible, it's just more difficult. So if you reverse the order of integration, then you're integrating with respect to x first. And then the y can be pulled out here. Now, this is where a very common mistake happened. Because you all know that the integral of e to the u is e to the u itself. But when you throw in a constant, because now I'm integrating with respect to x, y is therefore treated as a constant. And a lot of people mishandle that constant. So for instance, what is the integral of e to the 2x? You divide. All right, and I will shout this from rooftops if need be. Divide by the coefficient of x. Whether it's e to the 2x, cosine 2x, sine 2x, any function of a constant times x, when you're integrating, you divide by the coefficient of x. If you're differentiating, you multiply it. Again, it's always backwards. So yes, 1/2 e to the 2x. So what happens in this case is the integral of this is e to the xy divided by y. And the y's cancel out. And then you have to substitute the limits, x equals 1 and x equals 2. So you get e to the 2x minus e to the x, and then you can take it from there. Yeah. All right, so this is what becomes of now and then. It is a really good idea to integrate in the opposite order than what you might first think of. Any questions on this one? All right. The next one really was a spherical coordinates problem. That had basically a telegraph result. So e to the x squared plus y squared plus z squared, all raised to the 3/2 dv. And you're basically integrating over the upper hemisphere. So there's your upper boundary, is equation of the sphere radius 1, and your lower boundary is the xy plane, which is the same as z equals 0. in spherical coordinates, because I saw some people doing a lot of plugging things in, because I gave you formulas for x, y, and z in spherical coordinates on the formula sheet, but the best formula from there to use would be the fact that rho squared is x squared plus y squared plus z squared. This equation in spherical coordinates is just simply rho equals 1. Because what is a sphere? A sphere is a set of all points in three-dimensional space that are a fixed distance from the center. So this is something very important to keep in mind about spherical coordinates. And that makes it very easy to rewrite the integrand, because now this is just rho squared. And then rho squared to the 3/2 would be what?
Rho cubed.
Rho cubed. So, all right, now your limits, you're going all the way around the upper hemisphere, so 0 to 2 pi in theta. What about phi? What range of angles do you have there? 0 to what?
Pi.
No, pi over 2. North pole to equator, 0 to pi over 2. And then there's a sphere of radius 1, so 0 to 1 in rho. And then your integrand is e to the rho cubed. And then your extra factor, which you can get from formula sheet, rho squared sine phi. And then d rho d theta. Okay, so that's the setup. And once again, a substitution. Just be prepared to use substitution almost all the time. Well, because I don't want to put in there, I shouldn't say this, but I don't want to put in there something really nasty like integration by parts or, God forbid, trig substitution. This isn't a Cal 2 test, but what's terms of is a lot of people seem to have forgotten a lot of our Cal 2. And I don't know how you can expect to succeed in Cal 4 unless that is solid. So you can make substitution, u is equal to rho cubed, so then du is 3 rho squared d rho, and then the integral with respect to phi is a sine phi, and that won't be a problem. Oh, that reminds me, I forgot. Back to the previous problem, number 4, a very common mistake. People took e to the xy and forgot their laws of exponents and wrote it as e to the x, e to the y. That is wrong. What is this really equal to? Add the exponents. Yeah. When you have a product, okay, so that's what you have. When you have a product of exponents like this, you could write that e to the x raised to the y power, or vice versa, although that wouldn't really help you for this particular problem. Okay. I've said it before, one of the most common causes of mistakes are people simply getting mixed up between properties of addition or multiplication. Okay. All right. So that's really the interesting part of this one. Any questions about the setup for that one? Okay. Number 6. All right, so there are 3 things I was looking for. One is, did you get the right limits, which most people did? Did you rewrite the integrand correctly, the e to the xy? And then did you get the correct Jacobian? And I gave partial credit based on that criteria. So even though this domain is a very different character than the one in the practice test, the general procedure is still exactly the same. It's only the algebraic details that are different. So you have u is square root of xy, b is square root of y over x. Okay. You have these, so a boundary of region D is defined by these equations. Square root of xy equals 1, square root of xy equals 4, square root of y over x equals 1, square root of y over x equals 3. And you're already told, since you're already given that these are equal to u and v, those tell you the limits. So u is between 1 and 4, and v is between 1 and 3. So you're going to have those as your limits. The But then you have to take e to the xy. So how do you rewrite that exponent? And also how do you do a Jacobian? Now for both of these tasks, you need to go from these equations to x equals something, y equals something. And the way you handle that, in the practice problem, you had linear equations, and you could do elimination and substitution. Here again, you can do elimination and substitution, just dealing with products instead of sums. So for instance, if I take u is equal to square root of xy, and rearrange that to solve for x, let's say. So I have u squared is equal to xy, so x is equal to u squared over y. But now I can take this and substitute it into the other equation, the one for v, and I have, okay, so square root of y over x, so that would be y squared over u squared, once I simplify as much as I can. So now I have v is equal to y over u, therefore y is equal to u times v. So I've gotten that far, and then I can take this and substitute it back in here to solve for x. So x is u squared y, so uv, so I get u over v. So now I can rewrite my integrand. So x is equal to u over v, y is equal to u times v. The v's cancel, and you get e to the u squared. Now the only thing left is, okay, I'm going to have dv du, and I need to have my Jacobian, which comes from partial derivatives of x and y, with respect to u and v. So I can go back to these equations. So that would be xuyv minus yux_v. And so differentiating those with respect to u and v. So for instance, dx du would be 1 over v. dy dv would be u. dy du would be v. So it's just like partial differentiation from before. You differentiate with respect to one variable and you hold the others constant. And then dx dv, what is dx dv? That's the only one that's really interesting. Because your v is in the denominator.
Negative u over v squared.
Yeah, it's because that's the same as uv to the minus 1. So you could use the power rule on that. So minus u over v squared. And then you simplify all that as much as you can, and you get 2u over v. So that is what goes in here, and the setup is complete. So I hope that, I mean, after seeing all this, if internally you're kicking yourselves right now, trust me, I've been there. Okay? It's a universal part of the process of learning these things that nobody's immune from. So if you're not sure, even after seeing this, where these steps come from, or why it should occur to you to proceed this way on related problems, similar problems like the ones you might see on the final, then that's something we should talk about, and that's something that is worth approaching me about. And also, since also very important that you're using the homework in the right way to prepare you to do these things by yourself on a test, because I know that view an example feature is very handy, but if you're not truly digesting why, if you're following along with that, why they take steps that they do, you have to keep in mind this is something you're expected to replicate on a test. So resources like that, or other resources, including my notes, textbook, whatever, all very helpful if and only if used in the right way. Is there any questions about any of these.
Do you believe that the practice test was of the same caliber as the actual test?
Are you suggesting that it's not?
It just seemed, the practice test seemed more simple than the actual test. And it just seemed a little bit misleading as to not what sort of information would be on the test, but the difficulty.
Give an example.
Well, I'll look
Yeah, if you're gonna make that claim, you should make it up.
I'm just glad it
Yeah.
gives us one, because
Yeah.
our teacher doesn't give us one at all, so.
well, yeah, it's helpful. It's just
It would suck if we
Yeah, you have to keep in mind the main reason why I give them in the first place. It's so we get an idea of what kind of questions are being asked.
It's like a guide, like to let us know, like give us examples of what could be on test.
Right. Yeah. Well, first of all, the way I came up with both sets of problems was we had faculty who taught this class get together, and myself and a few others, and took questions that we've given on tests in the past, and basically put them all together in a pot. We had a large pool of questions. So then I had them all broken up by section, and I pulled them from there. Now, I will say this: I absolutely did not intend for there to be any significant difference in difficulty.
I'll tell you what it was, like, on Friday when I took the test, it looked different than the practice test, but now that I see this, it's almost exactly the same.
Yeah.
Like, it just looked a little different.
Yeah.
Worded differently, but it was
And
the
if I
same.
sound like I'm getting my hackles up, it's because that is absolutely not my intent.
It was just worded different, it wasn't really different, because you worked on the same way we did the practice problems, but it was just slightly
Yeah.
worded
Uh,
different.
so
I left my practice test and I allowed people.
okay, because if anything, sometimes I would try to choose, given a certain section, I had a couple problems to choose from. I would put the harder one on the practice test. So yes.
Real quick, the e to the u squared, you multiply the Jacobian by that to into that, right? Or it's e to the u squared times the
Times
Jacobian.
2u, or yes, it is.
Yeah. Sure.
Yeah. So, because I have seen it happen where the instructor will give something along the lines of a practice test, and then they always pick like the simplest version of whatever problem, so that it doesn't really help. And I'm not going to tolerate that kind of insinuation just because I don't go about it that way. And if in other words, if there really is a difference, it's completely unintentional.
Well, I apologize for that insinuation. I just didn't see the correlation between practice tests and this test.
You need to look again. You need to look again.
That's just my issue.
Yeah, you need to look again and rethink. Because I made both tests up at the same time. I don't play that way. So, I mean, if you look back at the practice test later, and you still think there's a discrepancy, then by all means you can bring it to my attention. But I'm not going to let anyone in this room think that that's how I operate. Okay, now, whatever time we have left, so the first assignment from chapter 15, it's not due for a while, on line integrals. We might not get through the rest of the section today. So, way to find a line integral before of a scalar value function over a curve C, and the curve C is parameterized by some vector value function R of t. Where t is between A and B. And the way this is rewritten in a form that can actually be worked out is you substitute your parametric equations into the integrand. And then you have so ds comes from the tangent vector. So all this square root expression of dt, that is what ds is written as. Your limits of your parameter become the limits of your integral, and you work it out from there. Although that integral can be quite a pain, depending on what your curve is. And the way one application of this was for work by force f of x, y, z. So at every point along the curve, a force is being applied to the object to move it along the curve from point A to point B. It's given by f. And so then, by applying the formula work equals force times distance, and it's integrating on the curve, you get the work across basically all those little segments. Now, today, I'm going to generalize this a little bit. What if the force is described not by a scalar value function like this one, that just gives the amount of force that's pushing the object in that direction, but by a vector value function, big F of x, y, z. Because then the formula for work needs to be generalized a little bit. So work is force times distance. Now, that formula assumes that force is actually the amount of force that's being applied in the direction in which the object is moving. Which does not cover this case. So here's your object, it's going to be moving in this direction, and I'll call the direction of travel d, d for displacement. But the force is actually being applied not in the direction of d, but in this direction. So then the amount of force that's moving the object along the displacement vector d is not going to be simply the magnitude of f, because the fact that it's being applied in the wrong direction cuts into that force a little bit. So really, this, if I break the force down into vertical and horizontal components, is the horizontal component that determines how much force is actually being applied to move the object in that direction. So if this angle theta here is the angle at which a force is being applied, then okay, I'll blow this up a little bit. So the length of this side, which indicates the amount of force applied in the direction of big F, that would just be the magnitude of F. But what we really care about is not that, but the magnitude of this piece that's going in the same direction as D. So how can I express this in terms of the total amount of force and also the angle theta?
You do F cosine theta times D. You get the work done?
Well, the amount of force is magnitude of F, cosine theta. Yeah, and then you multiply, because now this force and this displacement are going in the same direction. So yes, the work is equal to that force and multiplied by the magnitude of d. But how can we express that more simply?
The dot product of it.
It is the dot product. So we don't even really need to know explicitly the angle. It's a dot product of F and D. That gives us a work. So now we want to take that into account and figure out how to use this kind of line integral to figure out the work. Oh, maybe. Okay, so now if we are going along some curved path, and we break it down to little segments, then the work done would be the dot product of F times basically the vector between these 2 points, which I'll call delta S. I referred to it as delta S before as it's strictly a length, but I put a vector sign on it because now we're in the direction of that line segment. So I can write it like that. But I want to separate the magnitude from the direction in here. So now the magnitude of delta S, because we have a situation like this where we have delta S, change in X, change in Y. So that would be the square root of delta X squared plus delta Y squared. And I could, as I did before, multiply and divide by dt, the change in my parameter. Okay. And that leads to, as delta t goes to 0, I get square root of x prime of t squared plus y prime of t squared. So now what I'm going to do is, because I could write this as magnitude of F, magnitude of delta S, as a cosine of the angle between them, but that's the same as writing this as F dot product of the unit tangent vector and because I divided by the magnitude, I still have a magnitude again out here. So in terms of writing this as a line integral, so the work, what I really want to express is the work done along just one segment is using a more general formula I gave a little while ago, dot product of F and D, the displacement. So this is corresponding to D here. So now if I add up the work done along all the segments, what I really have is the line integral from A to B, and now my integrand, which before was just a function little f of x, y, z, I would now have f dot product of the unit tangent vector, and all of this depends on x, y, z, and then this right here is my magnitude of delta s. So I'm now going to have this right here is the same as the magnitude of my tangent vector times, sorry, forgot the dt earlier. So this is just the magnitude of my tangent vector, because your curve is described by, same way, r of t is x of t, y of t, z of t. Therefore, a tangent vector is this derivative of that, x prime, y prime, z prime. Okay. So what I'm doing here to get to work along one segment is I'm figuring out how much force is really going in the direction of a curve. And to get that, I'm just looking at the dot product of my force with my unit tangent vector, and then separately I take into account how far am I moving it along that segment. Well, the length of that segment is the magnitude of my delta s vector. Okay. So now this is my function little f from before of x, y, z, and that is my force in the direction of travel along the curve. And then I have the same expression that I had before. That we saw in the other kind of line integral. And keep in mind, this is the same as, here I did it in 2 dimensions, but the same idea. This is the magnitude of my tangent vector dt. But the thing is, now what we can do is cancel out these magnitudes. So we actually don't have any square root expressions to deal with anymore. So the total work is now just going to be the integral of big F, x of t, y of t, z of t, dot product with the tangent vector itself. So dot x prime of t, y prime of t, z prime of t, dt. So this is the line integral over a curve and it's abbreviated this way, f dot dr, where r gets a vector symbol. So this is how you compute the line integral of a vector field. So this section includes 2 formulas for line integrals. So this one right here, and then the other one right here. Okay. So let me address real quick, how do you know which one to use? Because they're used for completely different kinds of functions. So what we have right here, this is what I covered in the previous section, that you might have been tuning me out for because of the test. That's a vector field. So it has components, x of t, y of t, and possibly z of t if it's 3D. And this is what we're actually more interested in because of applications. I really mainly went through the other one just to derive this one. So like you're more likely to see this, in a test or homework. But it's good to see how it relates to the other one. This one, your integrand, is just a scalar valued function. Okay. And those were ones that's the one that I did some examples of already. And I think we're getting low on time. Yes, we are. Okay. So what I will do is on Wednesday, I have some examples of the other kind of a vector field for work when the force is a vector value quantity, and how those can be worked out. So, okay. And the homework's not for this question section is not due for another week. So.
Just the one that's due. Oh no, it says 7 days. Sorry,
Yeah.
that's next 7 days.
And don't forget to vote.
I don't vote.